Good afternoon, everyone. I'm just testing whether everything is working. If the video is coming through. Okay, it seems to be streaming by itself now. Okay, good afternoon, everyone. My name is Mr. Lucian Pullen. Well, you don't have to add the Mr. part, just Lucian Pullen, and I will be your tutor for today. And this will be my last session for this semester, and I will be handling or dealing it or this tutoring session will be about temperature and the first law of thermodynamics, but mostly on the temperature part and regarding the ideal gas law and the generalized gas law. Okay, now I know you don't go into this much, so I will go through all of these problems that has been assigned for my session. Now, if you have any questions, just raise your hands and we will answer these questions. Okay, I see there are no questions, so I will continue. Question 1. 48 grams of oxygen. So we have 48 grams of oxygen. I just wrote 4 grams. 48 grams of oxygen. 48 grams of O2 at room temperature consists of how many moles? So how many moles are there in 48 grams of oxygen? Okay. Now, oxygen is the chemical formula of O2. That's oxygen. It's a diatomic gas. Now, how do we calculate the number of moles? Okay, so the number of moles would be equal to mass, the mass in grams, divided by the molar mass of this molecule. Now, what is the molar mass of oxygen? Okay, it is 2 oxygen molecules. What is the molecular mass, the molar mass of one oxygen molecule? It's 16 grams per mole. So one oxygen molecule is 16 grams per mole. Let me just see if it's still fitting on the screen. Okay, let me rather write it this way. One oxygen has a molar mass of 16 grams per mole. Therefore, 2 oxygens or O2 would have a molecular mass of 30. So therefore, O2 would be 16 grams per mole multiplied by 2. So that is 32 grams per mole. So if you want to calculate the number of moles in this oxygen, in this gram, on this 48 gram of oxygen, we say 48 grams of oxygen divided by 32 grams per mole. And that, if you do dimensional analysis, the grams will cancel out and your answer will be in mole, which is what we want. Okay, now 48 divided by 32 is 1.5 mole. So there is 1.5 mole oxygen in 48 grams of oxygen. There's 1.5 moles of oxygen in 48 grams of oxygen. Now, you can actually calculate the amount of particles in there because 1 mole, or rather 1 mole of particles, 1 mole consists of Avogadro's number of particles, okay? 6,022 times 10 to the 23 particles is in 1 mole. So that is, you multiply that by Avogadro's number and you get the number of particles. Okay, that's just something you should have done in your chemistry or physics in high school. Now, question number 2 is to deal with pressures. Not pressures, pressure. Should have pronounced correctly there. Pressures. Okay. A bubble and diameter. Okay, I have found that students have a bit of difficulty with ratios and stuff. So let's say this question says a bubble having a diameter of 1 centimeter is released from the bottom of a swimming pool. So we have a swimming pool, and at the bottom we where the depth is 5 meters, we release or create a bubble. Okay, blow a bubble at 5 meters below the surface. Excuse me. What will be the diameter of the bubble when it reaches the surface? Okay, so what will be the diameter of the bubble when it reaches the surface? And they also tell us that the temperature of the water at the surface is 20 degrees Celsius, whereas it is 15 degrees Celsius at the bottom, so it's colder at the bottom, which makes sense. The density of water is 1,000 kilograms per cubic meter. Now, first of all, we need to find out what is the pressure at the bottom of the pool. And we know this from this law. The pressure at the bottom of the pool is equal to the atmospheric pressure plus the density of the water multiplied by G times how deep it is. Okay, let me just see if I can make this screen a bit smaller. And the movie there. Okay, I'll keep it like this. Okay, that should be big enough. So this is one. I'll do the answer in pascals. This is 1,013 times 10 to the 5 pascals, plus, that is the atmospheric pressure in pascals, plus 9,8. The density is 1,000. I'm going to write it here. That's 1,000 kilograms per cubic meter multiplied by 9,8 multiplied by the height, which in this case is 5 meters, and you get the pressure at the bottom of the pool. This is 5 meters here. Let me just make it smaller again. That's 5 meters and move it up. Okay, so that's 5 meters. And what you've been giving, or what you get at the end, is the answer is 1.503 times 10 to the 5 Pascal. So this is the pressure at the bottom of the pool. Okay, 1.503 times 10 to the 5 pascals. That is the pressure at the bottom of the pool. So now we know what the pressure at the bottom of the pool is. You know what the pressure at the top of the pool is. We know what the temperature at the bottom of the pool is. We know what the pressure at the top of the pool is. And we can now calculate the volume. We know what the volume is at the bottom of the pool. We can then calculate, using the general gas law, calculate the volume at the top of the pool, and therefore we would be able to calculate the diameter at the top of the pool. Okay, so we know now what the pressure is at the top and what the pressure is at the bottom. Okay, so the pressure at the top is P1, or rather the pressure at the top would then be the atmospheric pressure, and the pressure at the bottom would be the pressure you just worked out. Now the pressure at the temperature at the top of the pool is equal to, it's 20 degrees plus 273.15 Kelvin. To get it in 0.15, it's in Kelvin. That is 288,15 Kelvin. That is the pressure at the top of the pool. Now the pressure at the bottom, I'm just going to write bot. It's going to be 15 plus 273.15 equals, my notes, if I make it 293.15 Kelvin. So now we have the pressure at the top, pressure at the bottom, temperature at the top, temperature at the bottom. Now the volume at the bottom is the volume at the top, we want to calculate that. And the volume at the bottom, we can calculate that. Okay, the volume at the bottom, we can calculate that. Now I've already solved for the diameters and stuff like that. So the volume of a sphere is 4 over 3. Just remind myself, 4 over 3 pi, and the diameter over 2, and it's cubed. Okay. Now, this is the diameter that's been given. It's the 10 centimeters that we will be filling in here. And we can calculate that in the exact same way. The volume at the top will be 4 over 3 pi. The new diameter, we'll call this diameter at the top, over 2 cubed. This is diameter at the bottom. Okay. So we want to calculate the diameter at the top. Okay. So let's put this in using the combined gas law, which states that P1, P bottom, the pressure at the bottom times the volume at the, or rather the volume, yes, the volume at the bottom, the pressure at the bottom times the volume at the bottom over the temperature at the bottom is equal to the pressure at the top, volume at the top, and the temperature at the top. Now we've worked out the temperature at the bottom, temperature at the top, pressure at the bottom, pressure at the top, volume at the bottom. We can work out volume at the top. Now the reason why I haven't worked out the volume yet is because we can simplify it. Okay, we can actually simplify this law. Let me just put it in here that I'm going to do this. Pressure at the bottom, I'm just going to say B, and volume will be 4 over 3 pi d bottom. It's dB. When I write the B, it refers to the bottom. 2 cubed over T at the bottom, and that's equal to pressure at the top times 4 over 3 pi that's 4 over 3 pi, that's a diameter at the top, over 2 cubed, and you close the bracket, and that's the temperature at the top. Okay, now what you do know, or you should know, or should realize, that this can cancel, pi's can cancel, that cube there can cancel. It's just 8 over 8, and what you're left with is the pressure at the bottom times the diameter at the bottom cubed over temperature at the bottom, and that should be equal to pressure at the top, diameter at the top cubed, and over the temperature at the top. Okay, and that is how we will do it. Now we have this relationship. Okay, we have this relationship. We can actually now work out the diameter at the top based purely on the pressures, the temperatures, and the original diameter. Okay, so what was the formula? It says the pressure at the top, the pressure that I usually start at the bottom, the pressure at the bottom, temperature at the bottom, the diameter at the bottom cubed should be equal to pressure at the top, diameter at the top cubed over temperature at the top. Okay, now we want to solve for the diameter at the top. That is equal to, it will be the cube root of pressure at the bottom, diameter at the bottom cubed. You just rearrange the formula. TB, temperature at the bottom, multiplied by temperature at the top over pressure at the top. and the cube root of that. Now you substitute in everything that you have so far, and you should be able to get the answer. Okay, now of course that is a cube of the diameter, or you can write it there, or you can take it outside. Let's just leave it where it is right now. The cube root of that would be the pressure at the bottom. What was the pressure at the bottom? It's the pressure that we worked out. It's 1.5 times 10, 1.503 times 10 to the 5 Pascal, then multiplied by the diameter, which in this case I can keep it centimeters cubed, multiplied by the temperature at the top, which is 293 Kelvin, 0.15. Temperature at the bottom, the temperature at the bottom was 288.15. Pressure at the top, 1 comma, that's the atmospheric pressure, 0.13 times 10 to the 5. And if you work all of that out, you get that the diameter at the top in terms of centimeters is about 1.147 centimeters. That is the diameter at the top. Okay, so if this bubble bursts at the top, that would be its diameter. Let's check quickly. Now I forgot to do this for the previous question to just check the answer, but we can do it for this one. Remember our previous answer, what was it again? It was 1.5 moles. So let's check. Yes, the correct answer is 1.5 moles. We got an answer here for 1.14, or rather 1.15. Let's check if the answer is 1.15 centimeters. Yes, indeed it is correct. Our answer is 1.15 centimeters. Now a container. Next question. A container with a 1 liter capacity at 27 degrees Celsius. So the volume is 1 liter and the temperature is 27 degrees Celsius. Is filled with helium to a pressure of 2 atmospheres. So the pressure is 2 atmospheres. So that is 2 times 0.1 times 10 to the 5. And that is in newtons per meter squared, or rather a Pascal. How many moles of helium does it hold? Okay, this would be easy. I just want to check. No, not the answer. Let me just work out the problem. I just want to check here in my notes. Okay, first of all, we can convert to SI units. Okay, so 1 liter in cubic meter is equal to 1 times 10 to the negative 3 cubic meters. Okay, that is a liter in cubic meters. So you need to divide by 1,000. If you're in liters, you need to divide by 1,000 to get the cubic meters. Okay, now that is 27 degrees Celsius. So we need to go to kelvins. So we add 273. So plus 273.15. So let's just leave the 15 out. If we go there, that's 300 Kelvin approximately. Okay, you don't have to. I just make it easier because I can do the calculations easier this way. And then of course the 2 atmospheres of pressure. So we want 2 multiplied by 1 comma 1 times 10 to the 5 is 2. It's just simply, we just check there, is there, okay, it's simply just 2 times 10 to the 5 pascals. Right? There we have 2 times 10 to the 5 pascals. Now, what we usually do in this kind of case is we use the ideal gas law. Now, what is the ideal gas law? It simply says PV is equal to nRT. Okay, it's the most famous gas law. It's the ideal gas law. We make this T correct. There we go. P is equal to nRT. And they want to calculate the number of moles. So that will be PV over RT. You can then substitute everything in. So PV over RT. Okay. PV over RT. Let's see if I can fit everything in. The pressure is 2 times 10 to the 5 pascals. The volume is 1 times 10 to the negative 3 cubic meters. R is the gas constant of 8,314. And then, of course, we have the temperature, which in this case will be 300 K. Not writing in the units here. And if we work all of that out, the number of moles that you should get, if you do the sum correctly, is 0,08 moles. 0,08 moles. 0,08. Let me see if, of course, you could have used the other gas constant and then used it in liters, atmospheres. Instead, you'll still get the answer. 0,08. Let's see, that's 0,08. Let's check. Yes, that is correct. So this is the correct answer. Now, moving on. Question number 4. Question number 4. There is an auditorium. Okay. An auditorium, it has dimensions of 10 by 10 by 60. How many moles of air fill this volume at 1 atmosphere and at 0 degrees Celsius? Okay, so the temperature is 0 degrees Celsius. I just want to convert everything usually to the same correct units. Okay, I'm going to use the other gas constant. Well, it's the same gas constant, just a different version of it. So let's first write down the volume. Okay, the volume. It is a auditorium, so we assume it's a rectangular shape, or yes, a rectangular shape. So it'll be length times width times breadth. Ugly B, that's an L, that's a B. So it will be 10 by 10 by 60. So that's 100 square meters, and there is 6,000 cubic meters. If I'm not mistaken, 6,000 cubic meters. Now I want this the ideal gas constant. We've previously used it in cubic meters, so let's convert to liters and work it and use it in that form. So to get to liters, we just multiply by 1,000, so it'll be 6 times 10 to the 6, and the answer is in liters. Okay, that's the answer in liters. Okay, now we have the volume, we have the pressure at 1 atmosphere. That's 1 atmosphere of pressure. That is the temperature in Kelvin. It's 0 degrees Celsius, and Kelvin is 273,15 Kelvin. And the gas constant for this formula, okay, will now not be 8,314. This is the reason why I use this one. It's just to introduce you to the different versions of the gas constant. This one is 0, 0.08, 206, and it is in terms of liters atmosphere mole Kelvin per mole per Kelvin. This is the gas constant when you're working with liters, atmospheres, and kelvins. So in liters and atmospheres instead of pascals and cubic meters. Okay. So if you want to work out the number of moles, you have everything here. You have the volume, you have the atmosphere. PV over RT will give you N. So N would be PV over RT. And if you substitute everything in, the pressure is 1 atmosphere, remember. The volume is 1 times 10 to the 6 liters. The gas constant is 0.08206 liter atmosphere mole Kelvin. And of course the temperature of 273,15, and that gives you the number of moles. There's a big number of moles because it's a huge room. 200, if I'm not mistaken, 267,6. Oh, maybe I should round to 67,7 moles. This is the number of moles inside that auditorium, the number of moles of air. Let me check. That's 2.7 times 10 to the 2. 2.7 times 10 to 2. We rewrite this. This is 2.7 times 10 to the 2 moles. Let me just see if it's correct. I haven't checked this one. 2.7. Check. Why is that wrong? Why is that 5 moles? Oh, that is a comma error. That is not a dot. That is 267,000 moles. Sorry. That is wrong. That is not a comma I wrote here. That should be a comma, not a dot. So it's comma 2,700,690 moles. So if you rewrite this, this is why I never put commas in. Just leave it out. 1, 2, 3, 4, 5. So it's 2.7 times 10 to the 5 moles, which would make this one the correct one, number D. 2.7 times 10 to my mistake, therefore not being able to read my own handwriting. Okay. Question 5. Question 5. Okay, this is now has to deal with a thermometer, a mercury thermometer. I measure pressure, checking where we are for time. We're going to take a small break here. Just replying, someone wants to get some marks for me. Be with you guys in a moment. Okay, thank you. Patience, let me continue. Okay, first of all, a pressure of 10 millimeters mercury is measured using a constant volume gas thermometer at a temperature of 50 degrees Celsius. What is the pressure in millimeters mercury at 0 point temperature to 0 point temperature? Now, you need to first identify the relationship. A constant volume gas thermometer, okay, will use Amunton's law, or as you more commonly know, Guy-Lussac's law, which states that the pressure divided by the ratio of the pressure over the temperature at constant volume is equal to the pressure at some later time, the pressure at some later stage divided by the temperature at that stage. Okay, this is Guy-Lussac's law. Guy-Lussac's law. Guy-Lussac. It's his law. Okay, because it's a constant volume. Okay, volume is constant. C constant is the volume. Okay, now if we use this, they want the pressure at some other point. Okay, the initial temperature, you have the final temperature, initial temperature. The initial temperature T1, let's just, T1 is equal to, the initial temperature is 50.0, 50 degrees Celsius plus 273.15. That will give you your initial temperature in kelvins. That's 323 if I'm not mistaken. I don't do the stuff on the calculator, that you can do yourself. Just follow the method. The temperature at the end will be at the 0 point, which is 0 degrees Celsius, plus 273.15, which is just 273.15 Kelvin. So we have the initial temperature, we have the final temperature. What is the initial pressure? The initial pressure is 10 millimeters mercury. 10 millimeters mercury. What is the final pressure? Okay, or rather, yeah, the final pressure. So we want P2. Okay, this is P1. So we want P2. So how do we get P2? P2 is just P1 over T1 times T2. So P2 is equal to P1 multiplied by T2 over T1. So this is 10 millimeters mercury multiplied by 273.15 over 323.15. And if you do that math, you divide it, you multiply it, you get approximately 8.45. This is what I got, at least, millimeters mercury. 8.45 millimeters mercury. This is just simple math at this stage, but it's still nice to sharpen your teeth on. 8.45 millimeters mercury. And that answer is correct, as indicated by the correct mark in green. Now, at which of the following temperatures would 1 liter of water weigh the most? Okay, at which of the following temperatures Number 6, at which of the following temperatures would 1 liter of water weigh the most? Now, water would weigh the most at the when it has its heaviest mass, when its mass is the most. Okay. Now, where does water have its its maximum mass? Okay. Water has its maximum mass for the same volume of water. The volume is the same, but the density changes. Mass is equal to volume times density, right? Now, the volume is the same, it's 1 liter. Therefore, the density will change for the water. Okay, so at what temperature is the density of water the highest? Okay, at what temperature is the density of water the highest? What temperature is the density of water the highest? The density of water is the highest at 4 degrees Celsius. Okay, it's another wonderful properties of water. Its density is the highest at 4 degrees Celsius, which means its mass would be the most at 4 degrees Celsius, which continues to mean that uh, its weight will therefore be the most at 4 degrees Celsius. Now, I want to see if I can find density. There is usually a graph, density versus the density of water, right? Density versus temperature for water. There is a graph usually that they depict. Here, this is one of a good one, or I may rather see. Here you have it. Maximum density of water occurs at 4 degrees Celsius. Okay, water has its density, its biggest density at 4 degrees Celsius. Okay, so that answer is correct. So we can check 4 degrees Celsius. Let's check. Yes, it's at 4 degrees Celsius. Water will have its maximum density. Question 7. In order for two objects to have the same temperature, okay, this is now from your notes. In order for two objects to have the same temperature, they must be in thermal equilibrium. Yes. They must be in thermal contact. No. Doesn't even two things that are in thermal contact won't have the same temperature. This is part of the zeroth law of thermodynamics, ladies and gentlemen. They have the same relative hotness or coldness. Relative hotness or coldness is not defined. Have all the properties? No. Have only properties B and C. Okay. Only B and C. They must just be in thermal equilibrium. That's it. Okay. C have the same relative hotness. No. Let's just check. Yes, they must be in thermal equilibrium. Okay, then they will have the same temperature. So they must be in thermal equilibrium. The answer is they will have the same temperature only and if only they are in thermal equilibrium. In thermal equilibrium. Okay, question 8. One mole of gas. Okay, let me just take that. Question 8. 1 mole of an ideal gas has a temperature of 25 degrees Celsius. So N is equal to 1 it has a temperature of 25 degrees Celsius. So I will say, just check here, it's 25 plus 273.15. That is equal to 298. I'm just writing down everything as it's 15. Let me just check. Okay, then N is that. So we have the temperature T1. Let's call this T1. That's the temperature. Now the question is if the volume is held constant. Okay, so Gay-Lussac's law again, constant volume, and the pressure is doubled. So P1 is, let's say, we can randomly assign values to it, but we can just say P1, or rather P2 is equal to 2 times P1. Okay, that is what we've been told. If the volume is held constant and the pressure is doubled, the final temperature will be in degrees Celsius, of course. What's the final pressure? In degrees Celsius, we used Gay-Lussac's law. P1 over T1 is equal to P2 over T2. Now, we know that P2 is just double P1, so we can actually write that. So we can actually say that P1 over T1 is equal to 2 P1 over T2. Okay, P1 cancels, therefore we're left with 2 over T1, and that's T1. We want to find out T2. Okay, so if we want to make T2 the subject of the formula, we have that T1, or rather T2, because that's what we want the subject of the formula, we cross multiply. T2 is equal to 2 times T1. So T2 is equal to 2 times T1, and that's what the math shows, and it just makes sense because of the ratios. Okay, so T2 is equal to 2 times T1, and we just established that T1 is 298. 2 times 298,15 Kelvin, and that gives you 596,3 Kelvin. 596,3 Kelvin. And that, ladies and gentlemen, is, if you double the pressure, that is what will happen to the temperature. It will also double if the volume is constant, according to Gay-Lussac's law. Now 9, question number 9. I'm just checking my notes. 9, what does 9 say? Let me go to the problem, scroll to the problem here so you guys can see it as well. 1 mole of an ideal gas is held at a constant volume of 1 liter. Find a change in pressure if the temperature increases by 50 degrees Celsius. So if the temperature increases by 50 degrees Celsius, how does the pressure change? Okay. So the ideal gas law says PV is equal to nRT. Now, if there's a change in pressure, the volume stays the constant. N is 1 mole, it stays constant. R is a constant. Then the temperature will change. Okay? Therefore, the change in the pressure is equal to N times R times the change in the temperature over the volume. Now, if we solve or substitute everything we know so far to get the change in pressure, we have 1 mole of the substance, 1 mole. The gas constant is 0.08. I'm using the second one we used earlier on because it's in atmospheres. The answer is 0.08206. And the last one, we want 50 kelvins. Okay, the change in temperature is 50 degrees Celsius, and the change in temperature is the same as the change in Celsius is the same as the change in kelvins. So that's 50 kelvins, and it's 1 liter. Okay, that's why we used this constant. And if we work that out, we find that the change in pressure is 415. And it's, I think that's a comma again, 415,700 pascals. Okay, this should be in atmospheres. The next one is in pascals. So it's just 4,103 atmospheres. That is the change in pressures. 4,103 atmospheres. That's the change in the pressure. Okay, let's check here. There's an option for an answer of 4. So let's check 4 atmospheres. The closest one. Yes, we are indeed correct. It's 4 atmospheres, the change in pressure. Question number 10. Two bodies can be in thermal equilibrium with one another when they are at the same temperature, even if they, two bodies can be in thermal equilibrium with one another when they are at the same temperature, even if they, number one, absorb different quantities of thermal energy from their surroundings in equal time intervals. If they have different masses, yes, that is correct. They can, even if they absorb different quantities of thermal energy from their surroundings in equal time intervals, if they have different masses, if they have different volumes, yes, they can still be in thermal equilibrium. If they have any of the properties listed above. So D so far is correct. And if they have any of the properties listed above and one of them is in contact with a third body at a different, no, that is not correct. That will defy the law of the zeroth law of thermodynamics. So any of the properties listed above. So that is correct. Number D. Answer in this case, D, have any of the properties listed above. Answer, I'm not going to write that whole thing out. Answer is D. 11. 2 moles of an ideal gas are placed in a container of adjustable volume. When the measurements are made, so there's just 2 moles of an ideal gas, the pressure is inversely proportional to the volume. Pressure is inversely proportional to volume. That is Boyle's law. The temperature is directly proportional to the volume at constant pressure. That is Charles's law. The temperature is directly proportional to the pressure at constant volume. That is Guy-Lussac's law. All the statements above are found to be correct. D, all those statements are found to be correct. Only statement A and B, no, all of them are correct. That is the laws of gases. 12. In a 100-gram cube of ice, if a 100-gram cube of ice is heated from negative 120 degrees Celsius to positive 120 degrees Celsius, which of the following process is the greatest amount of energy absorbed by this material? Okay, now I have done this problem. Okay, it is in your textbook as well. You can check it out when you're converting a piece of ice to steam. The process that takes the most amount of energy is vaporizing steam. Okay, vaporizing water to become steam. Okay, it's a huge amount of steam. Okay, you can actually do the calculations, but we just know that it is that one. Okay, the correct, it is in your book. Okay, you can actually calculate it from specific heat and latent heats. Now the last one, number 13, we will do this one, the calculations, because it's interesting. Let's see. Yeah, okay. 13, yeah. A 100-kilogram student, 12, we already did. So number 13, a 100-kilogram student eats a 200-calorie donut. To burn it off, he decides to climb the steps of a tall building. How high in meters would he have to climb to expend an equivalent amount of work? So one food calorie is 10 to the 3 calories. Okay. Now convert the energy to joules. Okay. So 200 calories. 200 calories. You need to convert that to joules. Is equal to or rather I should multiply it at 4,186 joules. There's 4,186 joules per calorie. Those cancel, so your answer will be 200 calories is 836,800 joules. This is how many joules there is in 200 calories. Okay, now if he decides to climb the steps of a tall building, how high would he have to climb? Okay, so you will do the work formula. Work is equal to mass times gravitational accelerator times height. Okay, so the mass is 100 kilograms. That is 9,8. The height is what we want, and the work that we need to do is 836,800 joules. Okay, so if we solve for h, therefore if we solve for h, we will get how high the student must climb. That is approximately 853,88 meters. That is how the student must climb. 853,88, so 854 meters, and he will burn 836,800 joules. And that is correct. And that is all that we have time for today. Ladies and gentlemen, thank you for listening. I will see you next semester. Okay, all the best. Thank you.